So the goal in this video is primarily to figure out what is going on with molecules and how we can describe where electrons are with respect to those molecules and get us to those larger structures. So before we get into that, we need to address some of the known stuff that you should know prior to bridging this gap. So we've got those four things listed out with kind of their examples scattered around your electron configurations, the whole 1s2, 2s2, 2p6, etc. Atomic orbitals, what do they look like and what do they mean? Okay, so we're looking at probability spheres from quantum mechanical calculations. Bond types, which we've got kind of shifted into that lower right-hand corner. We've got ionic, polar covalent, non-polar covalent, which relatively minor, but then our other kind of bond type that we could reference would be single, double, or triple. And we'll look at the nuances of where those are coming from. And then finally, Lewis structures. We should actually be able to draw a Lewis structure. So if we're missing any one of those categories, you should go back and actually review that before moving into the video. So, where is this ultimately coming from? When we scale up from our atomic theory to molecular theory, we're making structures by having atoms interact and share electrons. So we want to understand how that's happening. And in atomic theory, we have electron orbitals to explain where our electrons exist. So if we were going to provide the valence electron configuration for carbon, could go all the way through it, 1s2, 2s2, 2p4, our valence shell would just be that outer part, our highest energy level. And if we applied that to kind of a representation of those orbitals, we'd have two electrons in our s orbital, and then we'd have one electron in individual p orbitals. Okay? And so we'd have our outer shell kind of explained. And if we went to look at the, say, structure now of a molecule that involves a carbon atom, say methane at the simplest, we would hopefully come up with a Lewis structure that would look along these lines. Okay. And now what we have to do is somehow reconcile these, because in the atomic theory we've explained where our electrons are in orbitals. Well, each of those lines is representing a bond, which is representing where electrons exist. And if electrons exist in orbitals and atoms, they need to exist in orbitals and molecules. So now the question is, what are those orbitals? Well, are they atomic orbitals? Can we get away with just saying they're atomic orbitals? Well, that's going to then come from some structural interpretation. The bond angle that we would look at within a Lewis structure would suggest we're at 90, and we know that to be false, okay, because that doesn't match the three-dimensional world. Okay? It actually has to be 109.5. Okay? And that comes from looking at our Vesper model of electron shell repulsion, setting us up so 109.5 degree bond angle within our methane. So how does that then reconcile back with our atomic theory? Well, we have four equivalent bonds, so we need four equivalent orbitals. So we go back to our atomic theory and say, well, do I have, four equivalent atomic orbitals? No, I don't. Okay. I've got 3 p orbitals, and I have 1 s orbital, So we don't have 4 equivalent orbitals, so that's problematic. Maybe our orbitals are at least properly aligned, and it's just going to be just a simple kind of rearrangement of those. Okay, well, we need, again, a 109.5 degree angle between those orbitals. Well, so the questions I like to ask is, what is the angle between an s orbital and a p orbital? And everybody has a hard time understanding that one, so let's skip that one for a moment and say, what is the angle between two p orbitals? Well, that angle is 90 degrees. Okay. So not only do I not have 4 equivalent orbitals, I don't have the proper bond angle or the orbital angle to match the three-dimensional structure. So that means something doesn't match. As I transition from an atom to a molecule, the orbitals change. That's the bottom line. They have to change. Okay? And that's where we get our nice kind of three-dimensional GIF showing the rotation. So this is ultimately where we come up with 2 new theories, okay, or models. Those models, number 1, hybridization theory, which in shorthand is really just magic, okay, or at least what it really seems like. Okay, and we'll address that. And then there's the kind of more quantitative method, which is the linear combination of atomic orbitals molecular orbital theory, or the Lacow-Mott theory, or Lacow-Mott, because it would be a bit repetitive to say theory. And while this one is super helpful, it typically requires the use of a supercomputer. So we have to kind of fudge between these two to get us both kind of some of the quantification that it becomes really useful in the Lacow model, but then some of the kind of qualitative, just magic hand-wavy stuff that we're getting in the hybridization theory. So let's start with the simple one, our hybridization theory. Okay, and we have to be careful here, because what we're doing within hybridization theory is not actually looking at a molecular orbital. We're looking at atomic orbitals that have been manipulated to contribute to molecular orbitals, okay, which is a bit confusing, but that's what's happening. So we've got our atomic theory, or our atomic orbitals with our S and our P, particularly for carbon. Okay, and now somehow magic happens, and we end up with molecular orbitals. Okay, but that magic is happening in very specific ways. Okay, and this is our hybridization. So what we're doing with our hybridization is mixing orbitals, our atomic orbitals, to make these molecular orbitals. Well, how do we know what orbitals to mix? Okay, well, that's going to come back to looking at our structure. So Lewis structure is still important. The number of orbitals that go into our hybrid, or our mix, must equal the number of electron groups. So if we pick the example that we've been working with, we had methane, okay, CH4, we have 4 electron groups. Okay? There's electrons, there's electrons, there's electrons, there's electrons. So 4 electron groups means I need 4 atomic orbitals going into the hybrid. Okay, so I go back to my atomic orbitals and say, well, where can I pull 4 orbitals from? Well, this is where this one's nice. There are only 4 orbitals in the valence shell, so all 4 must go in to be mixed. So I'm going to mix one of the S, and I'm going to mix the 3 Ps. And I'm going to mash them all together. So they're all going to go into a magic pot. And that magic pot is then going to mishmash them around, and then what we're going to pull out of them is 4 equivalent new orbitals. These cannot be the S orbital, and they cannot be the P orbital. They must be a new orbital, because the S and the P are atomics. Okay? So what we end up generating are these new orbitals. Those new orbitals will magically organize themselves according to our Vesper model. Once they're all equivalent, they will all arrange according to the shape that we would hope for methane, our tetrahedral shape. So we get these 4 new orbitals. And now the next kind of question comes in is, because we now have these new orbitals, we need to call them something. Okay? The name for these orbitals is entirely arbitrary, just like your name is entirely arbitrary. I can call these orbitals Bob. Okay? And I have 4 Bob orbitals. And while Bob is a lovely name, if your name happens to be Bob, that isn't very scientific. So what we ended up doing as scientists is said we need to come up with a better name. Let's actually name these orbitals from where they came from. Okay? Well, what made each of those orbitals? Well, an S orbital went into that, a P orbital went into that, and actually, in fact, 3 P orbitals went into that. So instead of calling each of those orbitals Bob, I'm going to call them sp3. This now distinguishes them from the S orbital and from the P orbital. It's just a name, just like Bob. It's a mash of those, and it just happens to look kind of similar to those. Okay? And by making these, I have 4 of them. Okay? Well, is there a situation where I don't have 4 electron groups? Yeah, I could have 3 electron groups. Well, then I'm going to take 3 atomic orbitals and try and mash them together. I could take the 3 P orbitals, because those are all equivalent. So why do we not do that? Because you'll notice our list says that we have to use the S and the 2P. This again comes back to our shape. If we had 3 electron groups, the bond angle is 120 degrees. The bond angle between our P orbitals is 90 degrees. Those don't mix. Okay? Those don't reconcile with each other. To get the bond angle to change from 90 to 120, we must introduce a different angle that's where the s orbital comes in. Okay? Or said in a slightly different fashion, when we're making molecules, we're trying to make the lowest energy molecule possible, which means, given the choice of these atomic orbitals, which of those orbitals should I always hybridize? I will always use the s orbital because it's the lowest energy. Okay? I'm trying to make a lower energy structure. So if the s orbital by necessity comes in, and I need 3 electron groups, that means I have to bring in 2 p orbitals. Okay? The result is I end up with 3 new atomic orbitals, 3 new molecular orbitals, and those molecular orbitals will get referred to as sp2. These are now different from the sp3 because they have 1 less p orbital. Okay? So instead of being Bob, these are now Sally. As an interesting feature here, though, if I started with 4 orbitals, I had better end with 4 orbitals, and I only have 3 orbitals shown here. Okay? But if you were watching really carefully, I actually erased the last one. Okay? We'll have a leftover p orbital that was not used in the hybrid. Okay? That p orbital doesn't disappear, it's still present, and it can still be used to contribute to bonding. Okay? The last possible option, at least as far as organic chemistry goes, is what if we have 2 groups of electrons? Well, because I don't think I've asked a quiz question yet, and it's been way out here, let's have you go through and try and predict what that hybrid orbital would be called and how many p orbitals would be left over. Okay. Hopefully now that you're back, what you should see is that we would need 1 s orbital and 1 p orbital, which would then mean we make 2 sp orbitals, and we would have 2 p orbitals left over that did not get touched or hybridized. Okay. We now have the possible hybridizations for organic chemistry, at least, that can be used now to explain our molecular bonding. One last thing I will point out that you won't see a quiz question on here, but you should at least reflect on it, is that if we compare the hybrid orbitals, so there's our hybrid orbitals, okay, there's our hybrid orbitals, and there's our hybrid orbitals. Okay, you'll also notice there's this little line there. Interestingly enough, if you notice, the orbitals are not all at the same space with regards to that line. Why? Let's try and come up with some explanations or looking at some examples. So let's look at the atomic hybridization for the center atom in each of these 2 compounds. Okay. If you would like to, take a moment and see what you can come up with. So first, we need to start off with our Lewis structure. BH3, very quickly, boron comes in with 3, hydrogen comes in with 1, there's 3 hydrogens, we have a total of 6 electrons, boron's our center. We would end up drawing out our Lewis structure, noticing that we had 3 groups of electrons. 3 groups of electrons turns into 3 orbitals. Since I have to use the s, that's going to go in, and then I will also have to use 2 p's. This becomes sp2, which means if I looked at my molecular orbitals, what I would end up with, okay, if we kind of spread them out away from each other, these are going to look kind of sloppy, but fairly accurate. That one was a little too big on that bottom part because they're asymmetrical. We would have our 3 sp2 orbitals, and we would have 1 p orbital left over unhybridized. Okay. We now have a description of the molecular, and that's in quotes, orbital for the center atom. We can't call it a molecular orbital because we're only referencing the center atom. We aren't referencing what it's connecting to. To get the molecular orbital, I must know the orbital that it's connecting to. Good question, probably one we'll save for lecture. Okay. So then the next one, we clear that away. What happens if we look at the center atom in CO2? I'm just going to jump straight to the Lewis structure. We would take a look at the electron groups around that carbon. Okay, we have 2 electron groups. We would end up with the hybridization of two hybrid orbitals where they were both sp, because we only needed two hybrid orbitals, and we would have two orbitals left over, and that would be the way this is drawn, our py and our pz. So all we've done is now explained or provided a hybridization for those. Okay. The easiest thing to do is to reference the red box, identify your electron groups, turn that into the orbitals of your hybrid, and that's really all you need out of hybridization theory. Okay? So why do we do this? Well, one of the reasons behind why we do this is that this magical just mix match, we know it needs to happen, also happens to explain some of the added characteristics of double bonds. Okay? If I'm going to make a bond, okay, I'm saying electrons exist there. If we look at the p orbitals, okay, this is my attempt at drawing the three p orbitals. I don't know why I had to draw them because they're already up there. Okay? They're not all occupying the same space. And in fact, that's one of the features of our orbitals. If we're looking at where electrons exist, they can't exist in the same space. Okay? And we can only have two electrons in that space. So how do we explain multiple bonds? Okay, well, the multiple bond says we now have four electrons in the same space, and I can't do that. So what's happening? Well, what's happening is I'm taking two electrons into an sp hybrid orbital to explain one of those bonding situations. The other one is being explained by a p orbital going into the other one. They're now not occupying the same space, because if we overlaid those where the nuclei is located, what I'm looking at, sorry, that was kind of horribly drawn. There's our p orbital. Bollocks. Let's just make that look prettier. There's our sp orbital, and there's our p orbital. This p orbital can now indirectly share with another atom and form an overlap, and then the other one can form an overlap with another one. And so we end up with two potential overlaps. In red, we have a direct overlap, which is an important word, and in the green, we have an indirect overlap, okay, which may be kind of weird. So, well, how can electrons do that? Well, electrons, according to quantum mechanics, can jump through space where they're not allowed to be. Lovely. That's what's happening with that indirect overlap with our p orbitals. Even though the orbitals aren't directly overlapping, they're close enough that the electron can jump to the other orbital. And if it's jumping, we now have a sharing between those atoms. We have that other bond. So our hybridization theory helps us explain that. And that's one of the reasons why hybridization theory has stuck around. Okay? So, interesting results that can come out of hybridization theory. So we will talk about this one also in class. Provide Lewis structures and the percent S character for the carbon, one of the carbons, their equivalent, in each of these three structures. Okay, so get your Lewis structure, look at the hybridization, and then define the percent S character, which I know sounds kind of weird, but do it anyway. See what you can come up with. We'll elaborate that in class and discuss why that becomes very important as far as the chemistry of that molecule goes. The next one is full-on molecular. Okay, so hybridization theory is kind of bridging the gap between atomic and molecular, but it never really jumps all the way to molecular because we're only looking at a single atom. We're saying we brought two atoms together, they somehow interact to make new orbitals. Those new atomic orbitals can make molecular orbitals, but we don't really define them as molecular quite yet. So to fully get to a molecular orbital, this is when we need some hardcore quantum mechanics, usually a massive computer, and a really smart person. And with those three things listed, we have absolutely none of them, at least coming from your instructor. Which means we're going to have to kind of come up with some way to finagle it so that we can understand it a little bit better. So, let's kind of take a step back, go back to our atomic theory, and think about what our orbitals are. Well, our orbitals were a probability density. of where the electron can exist. Okay? And that's a tricky concept, because we think electrons are particles. Well, they are, but they're also waves. Okay? So electrons have this kind of particle-wave duality, and it is that duality that makes them tricky to nail down, which is why we have quantum mechanics. Okay, so let's look at it kind of just that wave system. We've got two waves shown in this image. Okay? What I want you to do is think about the difference between these waves. We have wave A and wave B. See if you can come up with a difference. Hopefully what you noticed is that if we look right off that axis, that first wave, wave A, is in the positive direction, and wave B is in the negative direction. What we've just described is the phase of our wave. Okay? So what does that do for us? Well, our orbitals are really waves. So these waves, or these spheres, have a wave dynamic to them. If we now scale up to a molecule, what's happening when we look at a molecule? We're taking two waves and we're overlapping them. When those waves overlap, what happens? Okay? That's going to be our tricky part. When we look at our s orbitals, they are uniform in phase, but they can have either phase. They can either be positive, or all negative. So if we look at now bringing two waves in, so here's our parent wave, and it's now going to interact with a second molecule. Okay? So we have second molecule A as a possibility and second molecule B as a possibility. If we look at the parent interacting with A, what happens? Okay, and while I'm labeling, you can answer that. Okay. If we look at the parent with second molecule or second atom A, what is the result out of this? Well, since they are both in phase, positive, positive, what happens? Instead of having a nice kind of happy little line, we now have this massive amplitude line that is double the magnitude of what we started with. Okay? Which is saying we have a higher probability of finding the electron. Okay? So when we overlap, where they overlap is now, woo, big time. Electrons get really happy there. Okay? What happened if we ran into the parent with 2B? The opposite phase now, which means when we look at the result, all we see is a flat line, meaning where those two waves overlapped, they canceled, saying that the electron cannot exist there. Okay? So we have the opposite of electron density. Okay? Every time we bring orbitals together, we get two results. A in-phase happy thing and an out-of-phase bad thing. Okay? And it is those that are generating our molecular orbitals. Okay? So let's actually scale this out to our atom, and this is what we would end up seeing. Really what we're doing is looking at kind of a three-column format. We have the atoms on the outside, and in the middle, when we've brought these two atoms close enough to each other, we've generated the molecule. Okay. And really, we're looking at our atomic and molecular orbitals. So again, let's think about this. Let's say we brought our atoms in and they were both in positive phase. Okay? Where they now overlap, so let's draw it in the middle for the moment, that little section. And if we had our nucleus kind of dead in the middle, in that overlapping section, okay, if they're both positive, what have we done? We've increased the probability. Remember, the whole point of these shapes is a probability. So now we no longer have this shape. We have a shape that looks more along the lines of this. We've increased the probability of finding the electrons between the atoms. Well, if we have electrons between atoms, what do we have? Oh, snap. We have a bond. Okay? that bond is going to be lower in energy than the atomic orbitals that made them. And that might seem a bit challenging, but think of it this way. If it was not lower in energy, would we exist? Okay. The whole point of all kind of chemistry and atoms as we know it is to go to a lower energy state. If a bond was higher in energy than the atoms by themselves, we would never form bonds, which means we don't exist because we're not just a collection of atoms, we're a collection of bonds. So the bond must be lower in energy. Okay? This assumed so far that we were in phase, that they were positive and positive. But it could have just as easily been positive and negative. Okay? Well, what if it was positive and negative? We're still going to have the nuclei at roughly the same distance. Okay? Except now in that overlapping space, okay, the electron cannot exist. So what happens to our cloud? Well, it starts to look something more along these lines, where we notice right through the middle, we have no electron density, known as a node. Okay? A node is where electrons can't be, okay, or zero probability. This ends up being higher in energy. Okay? It's not going to be, or it's going to be higher in energy than the bond, because, well, the bond is low energy, and this time I don't have any electrons between atoms, so it's clearly not a bond. Should it be higher in energy than the atomic orbitals? Okay, well, the atomic orbitals that we're looking at are the zero interaction. They aren't communicating with anything. If we're looking at this new type of interaction, this is the atoms actively not interacting. Not passive, but actively not interacting. The analogy that I went through with another student is that if we look at relationships, you take a look at you and hopefully you're married, or if you're not married, just imagine you're married. Okay? You have you and your partner. Okay? When you're married, you formed a bond. What happens when you now interact with anybody who's not your partner? Okay? It's now no longer just kind of a, oh, we're just randomly bumping into each other. It's now you are actively trying to not marry them. Okay? Because you're already married. That's a higher energy state than if you were married or in a bonding situation already. Okay? So we end up now with two possible results. One case where we have a bond, and then one case where there's not a bond. Okay? But I didn't have a bond before either. Okay? This is actively not a bond. We end up referring to it as an anti-bond. Kind of like antimatter. It is the opposite of matter. When we then think about or connect everything, what we can do is typically see these lines connecting outwards. Okay? And very typically when we're looking at these, we ignore all of that orbital overlap, and instead what we reference is something that would look more along these lines. We have the lines representing our orbitals for our atomic. We have our line representing our orbitals for our bonding and anti-bonding. We usually see these dotted lines going out, okay, connecting this all up, and we now have a molecular orbital picture. Okay. Some things that come out of this. Number one, we started with 2 atomic orbitals. How many molecular orbitals did we end up with? 2. Yes, one is anti-bonding, but that's still a possibility. That is still a molecular orbital. It's just actively not bonding molecular orbital. Okay? So you start with 2, you end with 2. Every time we bring 2 orbitals together, we will also split evenly between bonding and anti-bonding. I can't have more anti-bonding than bonding, and I can't have more bonding than anti-bonding. Okay? So now the real power comes out of this, because in all of this, we did not define how many electrons were involved. So let's define it. Let's say our atom number 1 was hydrogen, and our atom number 2 was hydrogen. How many valence electrons does hydrogen bring into the picture? Well, each hydrogen brings in 1. When I now look at the molecular orbital picture, I need to populate the electrons that the atoms brought in into the molecular orbitals. Well, I will populate just like I did with the atoms into the lowest energy first. I will place 2 in. Okay? Now that I've got my diagram set up for my molecule, I want to evaluate just the molecule. What is the average result? Okay? Am I on average bonding, or am I on average anti-bonding? There's no anti-bonding, so my average is bonding. So guess what happens? H2 is a feasible molecule according to molecular orbital theory, which, interestingly enough, if we think about hydrogen, it is one of our diatomic elements. It fits, right? It does exist. Molecular orbital theory backs that up. Okay? And if you don't really trust that, then let's change hydrogen to helium. What is special about helium? Well, helium has 2 valence electrons. If we now scale this into our image, we still put 2 in the bonding, but we now have 2 in the anti-bonding. And one of the interesting features of molecular orbital theory, which is what our supercomputer tells us, is that the anti-bonding orbital is higher in energy from the atomic orbitals than the bonding orbital is lower in energy than the atomic orbitals. Which means, when I now take the average puts me somewhere above the atomic orbitals, puts me in the anti-bonding character, which means H2, diatomic helium, is not a feasible molecule to exist. And if we apply this back out to the real world, holy crap, diatomic helium does not exist. Molecular orbital theory supports all of that. Okay? This is why it's super, super helpful and valid and usable. Okay? The next one's looking at pi bonding. This one's significantly more challenging. What I challenge you to go through and do is attempt to determine the molecular orbital diagram for p orbitals now. We just looked at the s, so now look at the p. This scales up in difficulty significantly because you're now looking at 3 orbitals potentially interacting. Not only that, but the p orbital is even more challenging because the p orbital is not uniform in phase. It has 2 phases. One phase, arbitrarily positive, the other phase, arbitrarily negative. Okay? These are not charges, these are phases. Okay? So how do those stack and contribute to generate new orbitals, okay, or new molecular orbitals? We will work through this one in class, so hopefully you've got an attempt on it so that when we get to it, it'll make a little more sense. Okay. What can we do with this? If we scale this all the way up to a much more complicated molecule, say ethylene, C2H4, if we drew out the Lewis structure, which, by the way, you already did earlier in this video, we have this structure, okay, C2H4. The atomic orbitals that go into this, okay, well, each hydrogen contributes a 1s orbital. There's 4 hydrogens. Each carbon comes in, okay, well, there's 2 of them. Each carbon comes in with a 2s and 3 2p's. Okay, so our total orbitals, we've got 4 from our hydrogen, and then we have 8 from our carbon. We have a total of 12 atomic orbitals coming into our diagram. Okay. The rules that we said for overlap with the S ones still hold true, regardless of whether they're S or P. That means when I now shift the molecular orbitals, I must now split the atomic orbitals. Number one, well, actually, even before we split, if I have 12 atomic orbitals, I must have 12 molecular orbitals. How many of them are bonding and anti-bonding? When we bring 2 groups together, we get 2 results, bonding and anti-bonding. So that means my bonding and anti-bonding will evenly split out of the molecular orbitals, and I will have 6 anti-bonding, and I will have 6 bonding. Okay? If we scale that out to what your textbook shows, that's what they're trying to represent here. You'll notice that they don't draw diagrams for the sigma bonding. They show it only for the pi bonding. Okay? The pi bonding, we might say, well, what's going on with that pi bonding? Well, that pi bonding is actually referring to the overlap of the unhybridized p orbital? Well, a p orbital begins with the letter P. That was a super difficult question. How about pi? What does pi begin with? Oh, also P. Interesting. A pi bond comes from p orbitals. Okay. Well, what was the other one? The other option was a sigma bond. Okay. Well, sigma begins with S. What orbitals contribute to make the sigma bond? Okay. Well, the easiest one to look at here would be our hydrogens. Those were s orbitals. The other ones in between get a little bit more challenging. That looks like we have 3 equivalent orbitals all in a plane, okay, which would suggest 3 electron groups. What kind of orbital comes from 3 electron groups? Hybridization theory, those are our sp2. sp2 orbitals start with s. Our sigma bonds will always come from some s-class orbital. Okay? It can be hybridized in with something else, but it will always have an s orbital as part of it. Okay? What if we turn this into, say, acetylene? How many atomic orbitals would we expect out of it? How many molecular orbitals? How many bonding orbitals? How many antibonding orbitals? Okay? So look at each of those stages, see what you can come up with. There's going to be a quiz question now, and hopefully you got that right. Okay? We will come back, whether you like it or not, to molecular orbitals, okay? Because they help us explain where the electrons are in the process of breaking bonds and in the process of making bonds. Okay? So they are super, super important. Okay? So what we're going to do here really quickly here is we're going to push forward just a little bit, okay? And think about where we determined the molecular orbital bulk density to be located. So where was the highest probability found? Okay, and is that going to change our reactivity? Yeah. Okay, so what would a molecular orbital look like for the carbon-chlorine bond in chloromethane? So before we even address, we need to think about the hybridizations, because those are going to dictate the atomic orbitals being used. We need to decide the orbitals that are overlapping in this situation. Okay, we're overlapping the orbitals from atomic carbon and from atomic chlorine. Which hybrid orbitals from each? And then the last question, should they overlap evenly? That's an interesting dilemma too. Is there a difference between carbon and chlorine that would cause one of those to carry more electron density in the bonding situation, or to carry less electron density in the antibonding situation? Once we have a drawing of that, we can use that information to help us to predict something about the reactivity of this molecule, which we'll look at when we get to class. So with that, in under 40 minutes, you have the baseline for hybridization and molecular orbital theory. And I will see you next class period.